In this video, we want to prove that the cross product of two cross products exists in this form. So we want to prove this identity. I think this is now video 12 in our series concerning the SuperPowerful vector identities technique. Anyway, the playlist for all the videos is at the website digital-university.org. Now, in this video, we of course will make use of the epsilon delta identity, or at least we'll make use of a certain form of it. Let's look at our problem. A cross B cross C cross D, and again, as we stated in our previous videos, what we like to do is express the problem in component form. So we can call this A cross B. For right now, I'll call that vector F, and this we'll call vector G. So we could say that F cross G will equal epsilon, then we have FG times a unit vector, and we arbitrarily, it doesn't matter what we call it, but we'll call it I, and here we have J and K. So we have J, K, I. That's F cross G, and the ith component of this is just this. As we've gone over many times in our previous videos. So what we're going to do is take this away and just write this as F cross G, the ith component. Now, F itself is a cross product of A cross B, so we can write Fj as epsilon A B, get some expression like that. Let's go over to here. First we'll say F equals epsilon AB times some unit vector, and we are looking for an Fj component, so we'll label this J, and then for A and B, let's call this M and N, so this is epsilon MN J. And we know that this is F of J. So we're going to write it like this, take this away, and there's F of J. Now we want an expression for G of K, and G is this cross product, so we'd say G equals epsilon CD times some unit vector, and we want G of K, so this would be K here, and let's see, let's call this P and Q. So this would be epsilon P, Q, K. And again, we're really drawing heavily now from the work we've done in all of our other videos. We know that this is G of K. So just write it like that. There is G of K. So we have the ith component of F cross G, which is really this cross this. We have F cross G ith component equals epsilon jki f of j. But f of j is this. So we have epsilon m n j. AB AM B sub n. Times GK. GK is this. Epsilon PQK CP DQ. So this is what we have right now. Here we have 1, 2, 3 permutation symbols to deal with. And let's see, how can we arrange this? We have here epsilon jki, epsilon mnj, and epsilon pqk. Now, there's different ways that we can go about this. There's no hard and fast rule here. Epsilon jki we could write as epsilon. See, we could do it like this. This right here is the equivalent of epsilon k I j. This is an even permutation of this. We could just say epsilon kji. That introduces a negative sign. So let's have it like this. Epsilon kij. This and this have the same value because this is an even permutation of this. We have jki. Move the k over to here. That's one permutation. Shuffle the I over here. That's two permutations. So we can have epsilon kij in place of this. Then here we can have the k, shift that over to there. That's another even permutation. Epsilon k p q. This and this are equivalent because this is an even permutation of that. And if we do it like that, then we'll have an epsilon kij and an epsilon kpq. So that means we have two epsilons that share the first index. And that's the kind of setup that we need to invoke a version of our epsilon delta identity. Here, this is the form when they share a common I. Here's where they share a common K. Here we have IJLM. Over here, we're going to have different indexes. We're going to have IJ, P, and Q, but the pattern will be the same. And we've been discussing that pattern now ever since video 9. So here then, instead of JKI, we'll have KIJ. That's an even permutation, so there's no sign change. So this is Kij. And this PQK, we can have KPQ. An even permutation. And these indexes here still match the same order. Okay, now what we have is scalars where we're summing over from 1 to 3 and multiplying and adding. And again, since they're scalars, the order in which we do that is irrelevant. So we can write this as this will equal epsilon Kij times epsilon Kpq times epsilon Mnj A sub n, B sub n, C sub p, D sub q. Okay, now these two epsilons share the same first index. Now we can invoke our epsilon delta identity. And what will it be? Well, we know we're going to have two deltas, delta, delta, minus delta, delta. We'll fill in the blanks in just a moment for these indexes, but times this, epsilon m n j a sub n, b sub n, c p, dq. Now, what are the indexes here? Remember what the pattern is. It is inner, inner, so that would be IP, then outer, outer, so that's JQ, then for this one right here, it is inner, outer, IQ, minus outer, inner, JP. So we have these indexes then, IP, JQ, IQ, JP, operating on all this stuff. Now, first off, let's see what effect this has on this. So here, step number one, we have this pair of Kronecker delta symbols, and right now we're going to consider the effect on this. So here we have I has to be P, or that's 0, and over here J has to be Q. So this one right here will turn this J into a Q. This has no effect on it. So what we have then is we have this delta IP. This operating on this gives epsilon, and the J is now a Q. So we have, oops, get this into better focus. Okay, J has to be Q. So that's going to turn this to a Q. So we have M, N, Q. This has no effect on it because none of these indexes match. So this is still delta IP. This is now epsilon MNQ minus now we look at how this affects this. So here we have IQ. There's nothing like that over here. But here we see J has to be P. So that's going to turn this into a P. So we'll have delta IQ epsilon MNP. So this is a little bit different than what we've done in the past 3 videos. And then times A sub n, B sub n, C sub p, dq. Now before we go further, we should point out back here we did some symbol manipulations, perfectly valid, so that this and this shared the first index k. Or we could have done some manipulations so that J was here first and J was there first. We could have done it that way also. In the next video, we will do it that way, and that will give us a different expression, but let's leave that aside for right now. We just want to point out is that there's no hard and fast rules to which way you have to do this. For this video, we chose to work with these two. In the next video, we'll work with these two and invoke our identity. Okay, now here we have this expression. Now we have to consider what effect does this have on these scalars. So we have delta I P. So this is 0 unless P, well, we could say it's 0 unless I equals P, but there's no I over here. The equivalent statement is this equals 0 unless P equals I. And we have delta I, and that's 1. So that makes this an I. So we have epsilon MNQ AM BN DQ CI. Again, these have to match, otherwise it's 0, and it can be matched by the I turning into a P or by the P being an I. And we say let's make it match by the P turning into an I because we have P here to work with. So this now becomes CI. So we have epsilon AM BN DQ. That's epsilon MNQ. Then here we have minus IQ times this, and again we'll say let Q be equal to I. This gives an I right here, so we have minus epsilon MNP A sub n B sub n CP, and the Q turns into an I, so we have DI. So where we're at right now is that we're saying the ith component of F cross G, and F cross G is this cross this. We're saying the ith component equals this expression. Now here is where we're going to, again, rely on our previous videos. Hopefully you recognize what this is as we're running out of room. But that right there is A cross B, the qth component of it. So this is A cross B qth component of it. And I have this times D of Q CI. Now over here we have minus AM B sub n CP. Hopefully now from all of our previous videos, the work we've done, you realize that is A cross B and what's more, it is the P component of it. So we have minus A cross B times C of P times DI. So here we have A cross B P component times C of P times DI. Okay, now hopefully you recognize what this is. This is the dot product of D dot A cross B. And this is the dot product of C dot A cross B in component form. And it looks like, unfortunately, we've totally run out of room. So we're going to have to write this at the top of the board. But again, Q, this is component form for D, vector D dot A cross B. And this is component form for vector C dot A cross B. And notice that is what these are right here. Okay, but first we got to make some room. So let's go up to here. And again, we want to point out that in the next video we'll work this problem a different way. Instead of manipulating our symbols so that these have an identical index, we'll manipulate the symbols so these have an identical index, and then see what kind of expression we get. That'll be in the next video. Okay, we have this. And again, we're really relying on the work that we've done in videos 1 through 10, or 1 through 11 actually. Okay, we have this equals A cross B, the qth component of that, times dq times ci minus A cross B, that's P component times CP times DI. And this is component form for D dot A cross B. Times CI minus component form for C dot A cross B DI, and that equals the ith component of this. And if it's true for the ith component, it also has to be true for the j and the k component. Or what we can do is multiply both sides by this. So this is f cross g, the vector f cross g now. And again, we've been explaining that since video number 1. Equals D dot A cross B times vector C minus C dot A cross B. And this is vector D. So we have try to compare these two. D dot A cross B times C, D dot A cross B times C, minus C dot A cross B times D. And of course, F cross G, that's this. So there we have proven our identity. Okay, that's it for this video. In the next video, we will again tackle this problem and show how we can generate yet a different identity for it. And that will be coming up, I think, in video number 13 then. So stay tuned for that video and we'll continue our problem.